All right. So what we have today covers 13.2 in the textbook. This is section 1.2 in my notes. The section numbers will roughly correspond quite closely. Most of these calculus books, even for my notes, are set up the same way. So today's topic is functions of several variables. Okay. So this is where we start bridging the gap between what you're familiar with from Calculus 1, 2, and 3 and what you're going to be dealing with all the time in Calculus 4. So in Calculus 1, 2, and 3, you would dealing with a function of this form, just y equals f of x. And x would be referred to as the independent variable, which you can think of as the input, and y is the dependent variable. Okay. One thing is good, the main theme for today is notation and terminology. I'm going to be referring a lot of those things at you today, terms and notation that are going to be used all semester long. And it's very important that you get accustomed to these things. So when I write these things on the board or say them, you actually know what I'm referring to, or what, because the same notation is used in the main problems as well. Now, some other notation you would often, that could be used in Cal 1, 2, 3, which might not have been used very often in the classes you took, is we would say that the function f in this case is a mapping from some set D, which would be a subset of the real numbers, mapping into the, also mapping into the real numbers. And so the set D would consist of all possible inputs to a function that you can have. And what is this? What do we call that? Domain. That is the domain, which is why I'm using a letter D to refer to it. And any outputs would be range. Yeah. Now sometimes the actual range could be still also a subset of the real numbers. In fact, I'm going to be.
What does the colon between f and d stand for again?
It doesn't necessarily stand for anything, but in many contexts.
Is it like f is to d?
Well, it's really, this is a format that's used to state what the domain and range are. And then after that, chances are you would give like a formula.
Okay.
So actually, I'll throw out an example of this. Let's suppose we have f of x equal to x squared. So in this case, the domain, this is defined everywhere, would be all the real numbers. What would the range be? All possible outputs.
It would be all positive.
Yeah. And now I'm going to get a little bit picky, because it's a set of all. Well, because yes, you can include 0, and greater than or equal to 0. So in that case, we say non-negative. All right. Let's look at now. On the other hand, if we look at the function square root of x, well, domain and range would be switched, because now the domain x has to be non-negative, so x must be. And sometimes you can use a simple inequality or set of inequalities to define the domain. So x must be non-negative. Now in this case, well, actually, I would say the domain and range are switched because we have to make a choice of a positive or negative square root. By default, it's going to be a positive square root. So if I use y again to refer to the output, y also would be greater than or equal to 0. Okay. Now, there are a lot of problems on these assignment for this section where you're given a function and you're asked to specify what the domain is. And in some cases, the domain would be the entire space you're dealing with. Or sometimes you have to make some exclusions. And this applies whether you're talking about a function of one variable, like you are familiar with, or several variables, which I'm about to talk about. So it does no harm to talk about it now. So what I'm going to say here will actually help you with probably almost half the problems in the homework assignment, a lot of them. So finding domains. The simplest guideline I can give you is you can ask yourself, what can go wrong when you plug in a particular x? What are the circumstances under which a function might be undefined at a certain x value? So if you're given some function, what could go wrong?
Like tangent, if you were to graph tangent x, because you're going to have the asymptotes going the opposite way, so at those points, would it be undefined?
Yeah, so you can have, so what happens in this case, a function like tangent, actually all of the basic trig functions except sine and cosine, you have what are called vertical asymptotes. So tangent x, can anyone tell me what often causes a vertical asymptote? Now in this case, tangent is defined as, how's tangent defined in terms of simpler functions?
Sine over cosine.
Sine over cosine. So the vertical asymptotes are going to occur when what happens? What goes wrong?
When the ratio of sine and cosine cancel each other out, right?
Well, they cancel each other out, you go
Not
wrong.
cancel each other out, but
When cosine equals 0.
Yeah. So divide by 0. So that'll get you a few points in the homework right there. You can figure out where that happens. So this is one of the root causes of x value being excluded from a domain. Divide by 0. Okay. Let's hear another. What else can go wrong? What other sorts of operations?
If you had something like x squared plus 3 over like x minus 1, if
That's covered by this.
Okay, I was going to say that's not
Yes.
So if you're taking the square root of a negative number?
Yes, that's exactly what I was looking for. Yeah, so square root of a negative number. Okay. All right, and because I have an example about this in the notes, and this can also come up in the homework, this one is less obvious. So now we've talked to them about trig functions and algebraic functions and also rational functions for division by 0, algebraic functions like square root. Let's talk about different sorts of functions, exponential and logarithmic. What can go wrong there?
natural log is 0.
Yeah, so natural log of any non-positive. So like where square root your x could be non-negative, for a natural log or any logarithmic function, your argument must be strictly positive. Okay. Now there may be other things that can go wrong, but these will cover you at least for the homework. Look for these instances, find out where they happen, what x values are, or values of your independent variables are not allowed, and that leads you to what the domain of a function is. Okay. All right. Any questions about these issues? Okay. All right. Now, let's see. So what happens in this Calc 4 setting, where now we have more variables in play? Because this is what this course is. In fact, until a few years ago, this course was not actually called Calculus 4, even though it was the fourth course in the sequence. It was actually called Multivariable Calculus, which is a little more descriptive. So now you have a function which could be a vector quantity instead of just a number, like in this case. Your input, you still have a domain, but now that domain is a subset of what I'll refer to as Rn. So we're looking at n-dimensional space for your domain. So all of your points have n coordinates. And your function is mapped into some range, which is a subset of Rm. Okay. So you have, so these are still, so what's happening is, into your function, you're substituting n values. So these are your independent variables. Now you have more than one. And the output is going to be a point in m-dimensional space. M and n are allowed to be different. Okay. So you can imagine this complicates things quite a bit. So now, in this first chapter of the course, and I will get into this starting next week, when we're computing derivatives, what is a derivative? It's the rate of change of, you know, it's the rate of change of y with respect to x, but now we have multiple inputs, multiple outputs. So a derivative would now be a rate of change of one of these outputs with respect to one of these inputs. So you're going to have many rates of change to talk about. In fact, m times n of them all told. And that's why often it's helpful to use certain concepts from linear algebra, like vectors and matrices, to work with these things. Certainly we'll be dealing with vectors all semester long. Okay. Now, here's some terminology that I'm often going to use to refer to different situations, because sometimes we'll be back in the single variable land. Other times we may have n or m being equal to 1. So we have some simpler cases there. But as always, there's some jargon to deal with, and I want you to be familiar with that jargon. All right. So first of all, so I'm going to use the same notation as over there. So n, I'm also going to use to refer to the number of inputs, how many independent variables you have. M is the number of outputs. So with that in mind, if m, so the number of outputs is equal to 1, and we say that f, so when there's one output, I will generally not use the vector sign here. F is a scalar valued function. The scalar, the word scalar is often synonymous with just a number because it's often called a scalar because it's a quantity that can be used to scale a vector. So this term is used to refer to functions whose output is just a number, no matter how many inputs it might take in. So as an example, so any of the functions you dealt with in previous courses fall into that category. So f of x is equal to e to the x, or a function that takes in more than one input, so 3 in this case, but the output is just going to be a number. Okay, so that's a scalar valued function. Okay. If m is greater than 1, that is a vector valued function. So examples of that would be, you could have, now this is nothing about the number of inputs, only the number of outputs. So for instance, f of t could be a vector cosine t, sine t. So your input is just a single variable t for the time, And then your output is going to be a vector in 2 dimensions with x-coordinate, cosine t, and y-coordinate, sine t. Another example would be if I have a vector value function of 3 variables that has I'm just making one up. 3 components. Okay, just something like that. So here we have 3 inputs and 3 outputs. Now, this kind of situation where the number of inputs and outputs is the same is going to come up very often, especially in the last chapter of the course. So when we have a number of inputs equal the number of outputs, like here, and also more than one of them. So in other words, it's taking a vector in some dimensional space and mapping it to another vector in the same space. We call that a vector field. Because that's all it's doing, is mapping one vector to another, which can be quite convenient for visualizing such functions. Because I don't want to get to the point where I'm getting towards the end of the course and I'm talking about vector fields all the time, and you're like, what's a vector field? Here it is. Yes?
What does that mean, slope fields?
Actually, yes. Well, okay. Oh, like from differential equations?
I had it in high school calculus, AP calculus. It's the very end. I think we cut it up into 4, so
Yeah.
I'll see that's the same thing.
Well, let's see. Yeah, because I'm thinking in terms of like when you have the direction fields and
I think we just called them slope fields because we didn't have a concept of vectors yet in high school.
and I think the term direction fields is often used for differential equations to show the slope, to understand how differential equations behave. But yeah, because what's happening is at various points in your space, you have some vector of interest, and you're just plotting it.
Yeah.
So that's going to be familiar to you when we get to that last chapter. Okay. But when a slope field is more for a different purpose, vector fields can have many different interpretations. One of which is a slope, or a tangent vector of some kind. Okay. Are there any questions about the jargon or notation so far? All right. Notice here I'm using the angle brackets to refer to vectors, and so I was using that convention. It's often used in calculus books, but vectors can be written in various ways. So you could have like x1, x2, x3 using the angle brackets like I've just done, or sometimes parentheses, especially if it's a position vector, like to refer to a point in whatever dimensional space you have, or in the linear algebra world, it's conventional to write vectors as column vectors. It's a little cumbersome on the board, but it's out there. Out of curiosity, how many of you have taken Math 326?
Is that linear algebra?
Linear algebra. Okay. I figured some have, some haven't. One thing I like to do in this course, and I'm giving a disclaimer now so as not to freak out anyone who has not taken it. Linear algebra is very useful for taking concepts that you've already seen from single variable calculus and helping to understand the similar concepts in multivariable calculus. For instance, chain rule, classifying maxes and mins, and so forth. So I will talk about this perspective, but if someone has already taken linear algebra, that might be helpful to them. It is not a required part of this course. If you haven't taken linear algebra, you can just ignore that. That's the one and only time I'm going to give you permission to tune me out. It will never come up on a problem. It will definitely never come up on a test. But if there's anything that you should learn from the example I did on Wednesday, is that even though a math curriculum is segmented into these courses, and so you seem to be attempting to classify everything into topics. You have calculus over here, you have linear algebra here, differential equations, and then the god-awful modern algebra over here, things like that. It doesn't really work that way. All of these areas are used to contribute to each other. For a given problem, as I illustrated on Wednesday, you need to pull in other things. And that's why, unfortunately, math is very unforgiving when it comes to items we list as prerequisites. And most of the time, we consider those prerequisites very carefully. And I say most of the time because sometimes we're like, why is that listed there? So like this class was, I think, listed as prerequisite for 285. No, that doesn't make any sense. But the point is, unlike other subjects, if you've forgotten all that stuff, that's really going to hurt you. And at least early in the semester, I'm hopefully made you aware of that if you're not in good shape in that regard, if you've forgotten things because you've had plenty of time to forget, so that you're not blindsided when I start using these things again. For example, if I remind you that from Calculus 3, a dot product is a number, for how many of you is that news? Don't answer that. But if it is news, then I'm pointing out that there's an oncoming train, and you have time to deal with it. So, okay, and not a whole lot of time because later this chapter I will be using a dot product. Okay. All right. Now, I need to talk about visualization techniques, because when you have a function that only takes in one variable and outputs only one variable, you know how to graph, or you're supposed to know how to graph. In practice, not too many students do, because your minds have been corrupted by graphing calculators. But you know the process. You can plug in x values, get the corresponding y values, and plot those points and connect them with a smooth curve. Although, and in this course, visualization is going to be very important, but it's also going to be more difficult because we're often going to be working in three-dimensional space. Okay. But here's I guess you'd call this a pro tip. But when you do carry out graphing, let's suppose you're given some function, you plugged in a few x's and gotten a few y's, and let's suppose you got points, let's say like this. In these kind of classes, generally all the functions you deal with are nice, smooth functions. They don't have, maybe they have an isolated discontinuity or a kink in them, but for most part, they are smooth curves. So, and no, I don't expect everyone in this class to be an artist or anything like that. But chances are, if a graph of a function that happens to pass through these 3 points, and I see this sort of thing often on people's papers, it's not going to be something like that. It's going to be something nice and smooth, or something like that. So you get the idea. I've seen some very amusing graphs when it's happened. So, okay. Now, when you're dealing with functions of more than one variable, unfortunately, visualization becomes more difficult, because it's one thing to just draw a curve, but whereas the graph of a function y equals f of x, that's a curve, so that's no problem. What if you have z equals f of xy, so 2 inputs, now single output. So what's the next logical step up? So now we're one higher dimension than a curve. What do you think? What sort of animal would this be?
Like a bump. Is it a higher dimension than a curve?
Yeah. What did you say?
Like a cone or like a surface?
Surface. That's the term I'm looking for. I think someone said bump. That would actually describe many such surfaces, yes. Okay. Oh yeah, so you have a surface. So something like this. So I'm often going to be drawing these axes. So we have x axis, y axis, z axis, just by convention, with z going up. So we have positive x in this direction, positive y in this direction, and positive z in this direction. So if I limit myself to points x and y between, let's say, 0 and 1, so I'm using this square in the xy plane as my domain, so I just plug in points from here and get z values up here, then yes, a graph would be some sort of surface. So I'm going to be drawing lots of magic carpets like this. Or I might have domains that are, or surface patches that are have more complicated geometry than that. I'll often be drawing my generic blob or shape in peanut or something like that. Another thing to get used to. But to convey this surface accurately, it takes a lot more work than plotting y equals f of x. Generally, for y equals f of x, just a handful of points is enough to get a good impression of what the curve is like within a certain region. But it would take a lot more points plugged in down here to get z values up here to accurately describe or visualize this surface. So for functions of several variables, we have certain tools we use to fall back on curves. There are two approaches. Actually, only one of these comes up in the homework, but I thought I'd mention the other one too, because it could be helpful. So, we have a very important concept called a level set. So level sets of a function f which maps n inputs into a real number. So in other words, m equals 1. This is a scalar value function, so we're only considering that case. Is a subset of your domain for which, when you plug in these n variables, which I can also write as f of x, a vector x in n-dimensional space, equals k. So k is a constant. All right, so in other words, if your function is a, you can think of it as like a hypersurface, it's going to be sitting in n+1 dimensional space. So for instance, we have two inputs, we have a surface sitting in 3D, but you can think of it as an n-dimensional entity. By only considering the values of your x values for which you get a certain fixed constant k, so you are choosing k, what's happening is you're cutting it down to a n-1 dimensional space. So now this is how a level set is defined in general. So in a case where n is equal to 2, a level set is called a level curve. And this is what you've been dealing with in the homework. So what you're doing is, instead of trying to visualize the whole surface at once, you're going to pick certain constant values and find whatever curves cause this function to be equal to a certain value k. And what you can do is you can then select different values of k and get different level curves. And I'll show you an example in a minute. And if n equals 3, then you're looking at subset of three-dimensional space where a function is equal to a certain constant, and that's called a level surface. Okay, otherwise, we just call it a generic level set. Okay, now, before I give an example involving level curves, I want to point out that level sets in general of whatever dimension have some very interesting applications. For instance, there's a very well-known method, and it's something you can Google and find out more about, called the level set method, which is used to model how the interface between two substances changes over time. Often these substances are fluids. For instance, a more interesting example of what I'm talking about is, what if one of these substances is flame and how it interacts with the air? So how does a flame evolve over time? This is very useful for animation. So when you see these incredible movies or animation effects, it's actually mathematicians who play a role in making the animation so realistic. When I was at Stanford, I knew people who actually got to go up to Lucasfilm, which is just several miles up to the north, and actually be in the same building as George Lucas. And these people get movie credits and awards and so forth for helping to create these things. So all that animation, there's a whole lot of math behind it, and the level set method, which was developed by a very famous professor out at UCLA, who a very well-paid professor. He makes like $300,000 a year, but doing stuff like this. Because what we're trying to do is model these things more realistically. And yeah, it's great for movies, but certainly to help understand how these substances behave in reality as well. So in fact, what I've been told is that one of the hardest shots to do in any animated feature was from a first Shrek movie, pouring the glass of milk, the torture of a gingerbread man. So. Okay. So that's one of my yes, math is useful in the real world speeches. Okay. Now, so I want to do an example. Level sets, like level curves, level surfaces. Suppose we have a function z is equal to x squared plus y squared. So this is our function f of xy. So it's level curves of this function f of xy. So all you do is you set the output equal to some constant k. So if you think of k being a fixed constant and you're asking, well, what sort of x and y would satisfy this equation? So what kind of curve is that? What kind of curve does this equation describe? I know somebody here knows it. Yes, it's a circle. So these are circles. Where's the center?
0.
Yeah, the origin. What's the radius?
Okay.
No.
Or square root.
Yeah, someone does it every time. Can predict everybody's mistakes. Maybe I've taught this class too often. Radius is square root of k. So what you can do is, to get an idea of what the graph of this function looks like, which is a surface, so let's suppose I pick k equal to 1. Then your level curve is going to be a circle of radius 1. It's just a unit circle. So you go ahead and plot the unit circle, and you do it up here at this z level. So that corresponds to k equals 1. Then if I move up to, say, k equal 4, so the circle has radius 2. So I go up to this z level, and I have a circle of twice the radius. And I can keep going to plot more and more level curves. And if I have enough of them, even just a few of them, then if I want, I can connect them. This is a paraboloid. So it's a graph of this function. And you're accustomed to like y equals x squared, that's a parabola. We move up to another dimension, we call that a paraboloid. You're going to be seeing these functions often because it's quite easy to design homework problems around them. Okay. Let's see. On the other hand, well, first any questions about this one? If I go up one dimension, say w is equal to x squared plus y squared plus z squared. So now I'm talking about level surfaces. What would those be? What kind of entity? If I said x squared plus y squared plus z squared equal to k.
Sphere.
Yes, there's a sphere.
I have a question by the way.
Yeah.
Why are they called level surfaces?
It's just so only in the case where you have a function of free variables, that's if you have a function of free variables equal to a constant that describes it always implicitly describes a surface. Yeah. And I don't think there are certain special terms for any other number of dimensions other than 2 and 3. Okay. Now, okay, unfortunately time is running short. I'll mention this very quickly because it doesn't come up in the homework, but it's a useful visualization technique called sections. Now, in level sets, you're setting your output equal to a constant. Sections is the opposite. You set the input equal to a constant. So for example, back to our function z equals f of xy is equal to x squared plus y squared. So one section, go ahead and set x equals 0. So you get z equal y squared. Or you can set y equals 0. And you get z equals x squared. So if I were to, so now we have curves again in three-dimensional space, but different sorts of curves than what we have here. So for instance, if I have z equal y squared, and I'm setting x fixed at 0, that's my section. And then the other section, y equals 0, so that's, okay, this is x, this is y, this is z. So this is going to be hard to visualize from a board. So I have two parabolas perpendicular to each other. So this gives me, if I were to connect points again, I would again have a paraboloid. So drawing a few sections and drawing a few level curves would give you it kind of like give you a grid of your surface. So using both in combination can be very helpful to get a feel for how the surface behaves. And I'm surprised that actually the textbook we use now I don't think even covers sections, but I think they're just as useful with level curves. Okay. All right. I'll do one more example. And then you can pack up and go. Oops, I forgot to catch that on video, so anyone's watching can pause it there. I guess I have to be more careful about that. So for instance, if I have a function z is equal to x squared plus y to the fourth. So I actually have in my lecture notes, which I would recommend looking at, if I am looking down on the xy plane, if I go ahead and plot level curves, so for instance, I look at like k equal 1, 2, 3, and 4, because of the different degrees, what I have here is these ovals. So this is a level curve for k equals 1. And then again for k equals 2, and so forth. And so here's your view of your surface from above. But then what you would do is, if you could draw these curves at the appropriate z levels, so this would be located at z equals 1, z equals 2, z equals 3, then you have something like this at z equals 1, and then z equals 2. So it's not quite the same as a paraboloid. It's somewhat distorted because of the different degrees of x and y. But again, you can get an idea of what the overall surface looks like. Okay. And I think I'm missing the very page I actually needed. All right. Oh, yeah, this right here. Okay, so in the homework, there'll be certain problems where you give it a function, something like this, and you're asked to describe what the level curve's like. They might show some figures, and with the corresponding values of k, and you need, or refer to k as z, and you identify which figure is the correct one, things like that. Also, if you're not sure how to specify the answer to any of these problems, you have an option that says like to view an example, so it can show you, it can step you through a similar problem. So at least you know what kind of answer it's looking for. So I saw one case where it was necessary to do that. So get started on homework. Don't wait till the last minute. You're not behind yet, as I've said. So please try to keep that way. Yes.
Monday?
No, a week from today. You have oodles of time, but please use it. Bring your questions.